Welcome to the 10th lecture of course module Communication Engineering. So in the last lecture, we have seen the generation of the DSB-SC modulation. Before that, we have already seen how to, what is the time domain waveform of the double sideband suppressed carrier modulation and demodulation in the case of single tone modulation and multi-tone modulation. And we have already seen the generation of the DSB-SC modulation using balanced modulator. Now, in the today's lecture, I have to discuss about the one of the very popular method, which is ring modulator. Okay, for generating the DSB-SC signal. So let's see how this ring modulator works. What is the basic circuitry, and how the basic circuitry would be able to generate the double sideband suppressed carrier modulation. So in the last lecture, I have already explained about the balanced modulator. So please, those who are having any doubt regarding whether it is having output corresponding to DSB-SC or not because of this factor 2AC Ka, please do not bother about it. Okay, I have told you that YT is equals to AC MT multiplied with the AC cos 2 pi FCT, and here we are getting this another factor like 2 and Ka. Okay, so ultimately what we can write this equation as, we can write this equation equals to YT equals to AC dash MT cos 2 pi FCT. So these factors doesn't matter, you remember. Okay, 2 AC Ka. Okay, the thing is that we have to multiply the carrier with the masses signal. Okay, so please do not bother about these factors. So we can write this as AC dash MT cos 2 pi FCT. So ultimately it is having in the form of DSB-SC signal. Now we have to look at how this ring modulator works. So let's see this circuit. So first of all, in the ring modulator, we have this particular circuit. So you see this. In this circuit, we are having this transformer, okay, and another transformer is connected at this side. So from this transformer, we have the our masses signal which is connected here. Okay, this turn ratio may be 1:1. Okay, so basically the mass signal would be connected to this point, and then this other point will be connected to this particular circuit diode network. Okay, and then from this diode network, okay, the output would be taken from this. Okay, this particular second transformer. We are having two transformers. Okay, so these are basically audio frequency transformer. You remember that these are the audio frequency transformers. So whenever we apply any very high frequency, okay, at this particular carrier point, okay, generally this transformer act as an open circuit. Okay, I will be telling you later. So just see this one, this circuit first, okay, and then we are having one band pass filter at the output. Okay, so we have to look at how this circuit works. So if you see the connection, okay, you just try to see this connection, okay, of the diodes, how these diodes are arranged. So there is first diode D1, then we are having D2, okay, it is connected in this way, then D3 and then D4, okay. So this way it is connected in this circuit, okay. Now we have to look at, as we said that in the case of modulation, we need to have the message signal and then a carrier signal, and that two should be multiplied in a certain form, okay, to get the modulation or modulated output. So here we can see that this message is being connected from these two terminals, and then a particular carrier is being connected from this two terminal, okay. So here you can see that here I have written like A cos omega CT. So basically this carrier I can represent as CT, and that CT is actually this square wave. Okay, this type of a square wave we have to connect, fine. Instead of connecting A cos omega CT, we have to connect this particular square wave. Now if we connect this square wave, okay, the resultant output, you will find that we are going to get a DSB-SC signal, okay. So how it is going to give you the DSB-SC signal, that we have to look at. So basically what we have to do is we have to connect a very high frequency square wave, okay, symmetrical square wave we have to connect at this point, and we have to connect the message signal, okay. So let us say this is our message signal MT, so that should be connected to this two terminal. Now what we have to see is we have to see how this diode will get turned on and turn off, okay. We will consider that the diodes are ideal, okay, just for the simplification. of the explanation, we can consider these diodes are ideal. Okay, so whenever this particular terminal, okay, this point, you can say either a point, okay, this terminal A, if it is at more potential than the point C or terminal C, then this diode D1 will be forward biased. Okay. Similarly, because this is having the same point, okay, you can see here again. So basically, you try to understand here that the frequency of this square wave, okay, is very high as compared to our masses signal. Okay, the frequency of this particular masses, this particular square wave is very high as compared to our masses signal. And turning on and off characteristics, and it will be sufficiently large to turn on and turn off the diodes. Okay, so basically the turning on and off characteristics of the diodes will be depending on the this particular square wave. Okay, it won't be depending on the empty, it will be depending on the square wave. Means what is the polarity of the square wave, and that will going to control the turning on and turning off conditions of the diode. Okay, so how it is going to control that we have to look at. So let us suppose that when this terminal 1, okay, if we have connected this type of a square wave at this point, okay, as a carrier, high frequency carrier, then whenever this terminal 1 is at more potential than the terminal 2, then we can see that this terminal will be at more potential than this terminal. Okay, because it is connected to the center tapped point. Okay, so I can say that it will be having like same potential, A or B. Okay, it will be having the same potential. So whatever we this like point means the potential at the point A or terminal A. So if it is as more potential than this particular point, then we can see that this diode D1 will get forward bias, and sufficiently forward bias because of this potential, because there is a potential difference. Okay, and A will be at higher potential than the C. Okay, terminal C. Similarly, here again, this terminal B will be at more potential than the terminal D. Okay, so what I am saying is, whenever we are going to get this high value of this carrier, okay, this is square wave, okay, positive value of this carrier, which is sufficiently a large positive DC value. Okay, so that time the diode D1 and D3 will be forward biased. Okay, and the diode D4 and D2 will be reverse biased. As we know that how to decide the forward and the reverse characteristics of the diode, whenever the anode is at the more potential than the cathode, okay, it will be forward biased. And if it's a reverse condition, like if cathode is at the more potential than the anode, then it will be reverse bias. Okay, so right now we are considering this case 1. So what is this case 1? When terminal 1 is more positive than terminal 2. Okay, terminal 1 is more positive, means we are talking about this half. Okay, so it is more positive than the terminal 2. So this diode D1 and the diode D3 will be turned on. Okay, and it will be replaced by it's forward bias equivalent, means short circuit. So it will be getting short circuited, and then we can see that this empty, okay, this empty will be because of the transformer induction. Okay, this empty will appear across this two terminal AB, and then this will be ultimately appearing across terminal C and D. So finally, we are going to get the output at these two terminals. Okay, at these two terminals, right? That will be equals to empty only. Okay, whatever be the masses signal that we have connected, so that will be appearing across this particular terminals, right? Now, if we consider, okay, and we can also see that the diode D1 and D3s are actually, here I have written something wrongly, okay. So please, okay, so it is written right, okay. So it is D2 and D4, okay. So D2 and D4 are actually in the reverse bias condition. So you can see that it is open circuited, okay. It is open circuited because this terminal is more positive. So it is our cathode, and this terminal is more negative, okay, but it is your anode. Okay, so it is in the reverse bias, and the same you can think of about this diode D2. So it will be again in the reverse bias. Now we have to consider the case 2 when the terminal 2 is more positive. The meaning is we are talking about the negative half of this square wave. Okay. So if we talk about this negative half of this square wave, we can see that this negative, okay, this particular terminal 2 is more positive and this will be becoming negative. Okay. So when this is the condition, right? And that time what we can see, this is positive and this is negative. So this is connected to this terminal. Here we can see that. Okay. So this diode D2 will be forward bias. Okay. Similarly, again, this is positive. So this diode D4 will be forward bias. Okay. And this diode D1 and D2 will be, D1 and D3 will be open circuited because it is reverse bias. Okay. So this is going to give you an equivalent circuit like this. Okay, it will be going to give you an equivalent circuit like this. Okay, this diode D2 and D4 will be conducting and it will be replaced by its equivalent short circuit. Okay, and then these two diodes will be open circuited. Fine. So these are the two different cases. And now if this is the case, we can see that what will be the output of this transformer. Okay, what will be the output at this two terminal. So once we have applied the signal empty here due to induction, there will be a signal empty. Okay. Now this empty, whatever be the potential, okay, it will get reverse. Okay, because this point is connected to this and this point is connected to this. Okay. So basically there is a cross connection. Okay. So whenever it is a cross connection, we can see that when it is connected in this way. Okay. So this will be becoming positive now and this will be becoming negative. Okay, so earlier it was this point was positive and this was negative. Here again you can see this was positive and negative. It is again positive, negative, then positive, negative, and finally we were getting positive and negative. But in this case it is positive, negative, here positive, negative. Now this positive is connected over here, so it is this terminal will become positive and this will become negative. So finally we are going to get positive and negative. So basically what I am saying is in the second half, okay, of this square wave, the output of this transformer we are going to get as minus empty. Okay, it will be minus empty. So based on these two cases, case 1 and case 2, if you understood the working, okay, one thing that I would like to clear that basically these transformers are audio frequency transformers. Okay, so whenever we apply this type of square wave of sufficiently high frequency, generally this transformer will be act as an open circuit. Okay, so there might be a question like why means there should be an induction from this point to this point also. Okay, but it doesn't happens because of the design of the transformer. It is an audio frequency amplifier, audio frequency transformer, so that only this empty can be transferred from the transfer action, transformer action, okay, from this winding to this winding. Okay, but at the same time this particular transformer or this transformer will be act as a open circuit for this particular square wave, because at that very high frequency it will be acting as open circuit. Okay, this is how we actually control the designing. Okay, so after having this case 1 and case 2, what we need to understand is just seeing this one. If we have this square wave and if we have applied, let us say, the empty is of this form, okay, then by seeing these two conditions, we can we can write the we can draw the waveform at this two terminal. Okay, we can draw this waveform. So what I said, then when it is positive, okay, when it is positive half cycle, then the output would be empty. So whatever be the empty, okay, that empty will be going to appear during this particular duration. Okay, up to this duration. Okay, so up to this duration, this empty is going to appear. Fine, this empty is going to appear. Now when this is becoming negative, okay, at this point the output is going to be minus empty. Okay, so the same thing is going to be minus empty. Okay, here it is again, we are going to getting minus empty. Okay, the negative half. Again in the positive half it should be empty. So now we are going to get again empty, then again minus empty, then again empty, then minus empty, plus empty, and so on. Okay, so this way we are going to get our output, and whenever this empty is making a phase reversal, there will be a phase reversal of the carrier. Okay, so this product that we are going to get, again it will have a phase reversal at this point, 180-degree phase reversal. Okay, so this is our output. Okay, this is our output or the multiplication of these two waveforms. Okay, that will be going to appear across this particular terminal. You remember that it is the output at this terminal. Okay, this terminal. Okay, these two terminals. Okay, now this circuit is being followed by a band pass filter. Okay, so there should be a connection of the band pass filter. Now, one thing that we have to analyze here is that what will be the means time domain expression for this waveform. Okay, what should be the time domain expression for this waveform? And similarly, if we want to calculate what is the frequency spectrum of this waveform, okay, that if we understand, then only we will be able to tell after passing through the band pass filter, we are going to get the DSB-SC signal. Okay, so let's try to understand what will be the time domain waveform for this particular waveform. Okay, this waveform. So please do not bother about this. Okay, I have written like Vi equals to MT W naught T. So I have represented in the next slide this as a CT into MT. Okay, carrier multiplied with the mass signal. Okay, the same thing. So now you just try to understand that we have applied here the symmetrical square wave. Okay, so in any of the signals and system book, you will find that if we have any symmetrical square wave, okay, of this form, okay, its amplitude is 1 and -1, and then period is T naught. Okay, so fundamental period is T naught, right? T naught to T naught, this is the period. So its frequency will become T naught equals to 1 upon FC. Okay, so this is our square wave, and if we are having this symmetrical square wave, you can find out the equivalent Fourier series expansion of this particular square wave. Okay, trigonometric Fourier series. So you try to calculate the equivalent Fourier series representation, trigonometric Fourier series representation of this particular symmetrical square wave. So I'm just writing the final result. Okay, so that derivation for me is not important here. Okay, that you can find in any of the signals and system books, right? So this is my request from the viewers. Okay, all the students, please go through any signals and systems book and please see this waveform and try to get the trigonometric Fourier series. Okay, I am writing the final result of this type of square wave. So we have the CT, so that trigonometric Fourier series will be taking this particular equation. Okay, you will find this equation anywhere in the books. Okay, so this is our Fourier series representation of this particular square wave. That is nothing but equals to 4 by pi summation over n equals to 1, 3, 5. So all the odd harmonics will exist. Okay, so n equals to 1. So what is the, I mean to say, the harmonics? So there will be a fundamental frequency. Let us say the frequency of this particular square wave is FC. So that FC is the fundamental frequency. Then the multiplied, you can say that if we have another frequency component, okay, it may be a even multiple or odd multiple of the frequency components. Okay, that other frequency components will be called as the harmonics. Okay, so basically the first basic frequency component is our fundamental frequency component, for example FC. And if we again have any other frequency component like 2FC or 3FC or 4FC, 5FC, okay, those all frequency components will be called as our harmonics. Okay, harmonics. Okay, so basically CT is equals to 4 upon pi, and here you will find that in this particular square wave Fourier series representation, only odd harmonics is going to exist. Okay, only odd harmonics. So that will be 1, 3, 5, 7, and so on. Okay, and then it will be taking this form -1 to the power n minus 1 by 2 divided by n cos n omega ct. Okay, so when you substitute n equals to 1, it will be our fundamental frequency omega c, and then it will be 3 omega c, 5 omega c, and so on. So this is our CT. So when we have this CT, then multiplying this carrier with the massive signal, we are going to get the MT into CT. Okay, so basically just we have to open this summation. Okay, it will be an infinite summation. So if we open this summation, this factor 4 by 5 is outside, and now we can multiply the empty to this particular factors. Okay, so the first factor, if you calculate, you just substitute n equals to 1, you will be getting 1 minus 1, that will be equals to 0. So minus 1 to the power 0, that will be giving you 1, and then this is n equals to 1. Okay, then again it will be cos omega ct. So basically empty, if you multiply, the first term that we are going to get is empty cos omega ct. Similarly, if you substitute n equals to 3, you are going to get minus 1 upon 3 cos 3 omega ct plus 1 upon 5 cos 5 omega ct, and so on. Okay, so I hope here I have written, there is something mistake while writing. Okay, so here it is empty cos omega ct. So after minus 1 by 3, there should be empty should be multiplied here. Okay, empty cos 3 omega ct 1 upon 5 empty cos 5 omega ct plus n dash dash. Okay, so please in this equation make it correct. Okay, empty should be multiplied everywhere. Okay, so basically what we can see, this is the multiplication of this empty into ct. Okay, that means I'm talking about this waveform. Okay, this waveform. So the time domain representation of this particular waveform is this one, empty into ct, 4 upon pi empty cos omega ct. All the odd harmonics are present. Okay, so now again, if you want to directly, we can see from this equation itself. Okay, from this equation itself, what we can observe is if you apply the modulation property. Okay, we can see that the first component is nothing but your empty multiplied with cos 2 pi fct. Okay, 4 pi empty cos 2 pi fct. Then the next term is 4 upon 3 pi cos 3 omega ct. Okay, and so on. So basically what happens is, if you try to calculate the Fourier transform, okay, we have to apply the modulation property, and that is going to give you the shifted spectrum of your massive signal empty around fc. Here it is fc. For second term it will be around 3 fc, and then again it will be at 5 fc. Okay, so it is a shifted version of our Fourier spectrum of the massive signal. Okay, so I have already discussed so many times, so I'm not discussing it here. Okay, but you can easily calculate the Fourier transform here. Okay, by just following the modulation property. Okay, so there will be a shifted version of the spectrums of our massive signal. Okay, massive signal. Okay, so that I have plotted only the positive part. Okay, I have just plotted the positive part, just considering the massive signal like this. So the first, this first term is going to give you a spectrum around fc. Okay, so here is the fc. So our first spectrum will be like this. It will be fc plus fm, fc minus fm. Okay, what will be the magnitude? Magnitude will be 2 upon pi. Okay, you just verify it. You will going to get this value equals to 2 upon pi. Okay, now the second our component will be this one. Okay, our massive signal spectrum will be shifted around 3 fc. Okay, because it is 3 omega ct, it will be shifted around 3 fc. Now when it is shifted around 3 fc, you can see that its magnitude is becoming 1 upon 3. So whatever be the magnitude at here, it will be divided by 3. So here you can see its height is more, and here I have just plotted it, height should be less. Okay, it's 2 upon 3 pi. Okay, rather you can write minus 2 upon 3 pi. Okay, so it is inverted one. Okay, we are going to get the spectrum in this form. Okay, if you just plot the magnitude spectrum, remember that if you want to plot the magnitude spectrum, this will also means turn up. Okay, it will come just above this 0 line. Okay, in this way. Okay, just you have to take the mirror image of around this particular x-axis. Okay, so if it is just magnitude, if you want to consider, but here I'm not considering just the magnitude, I'm just also denoting the Fourier spectrum considering the sign. Fine, so it will be a negative, so minus 2 upon 3 upon pi, minus 2 upon 3 pi. Okay, and it will be shifted around 3 fc, so 3 fc plus fm and 3 fc minus fm. Again, if you consider the next one, its height will be reducing again. Okay, so now it is having less height. Okay, it is a plus sign, so we are going to get 2 upon 5 pi, 2 upon 5 pi, and then it is shifted around 5 fc. Okay, which is 5 fc plus fm, and it is 5 fc minus fm. and so on. There will be infinite number of such bands will be there. Okay, infinite number of such bands. And the thing is that its height is going to reduce as we go on plotting the higher harmonics, odd harmonics. Okay, because they are all the odd harmonics, 5 omega c, 3 omega c, 7 omega c. Okay, so its magnitude is going to be reducing. Fine. So the same image you can also plot at the other side. Okay, the mirror image at the negative frequency side. So this is what our spectrum of this particular MT into CT. Okay, frequency spectrum. Now we can understand that if we are having this type of spectrum, okay, this type of spectrum, just having a sufficient band pass filter, okay, if we are having a certain band pass filter of sufficient central frequency and bandwidth, okay, so we have to design a band pass filter to just select this component, okay, if we want to have our carrier frequency equals to omega c. Fine. If we want to have our carrier frequency equals to omega c, or you can say fc, then we have to select only this portion. Okay. If you want to have the carrier frequency equals to 3fc, you can select this portion. Okay. This is the beauty of this particular equation. Okay. It will be completely depending on your need. Okay. So if you want to just select this portion, then obviously we need to have a band pass filter, which is here in this block diagram, it is represented. Okay. So we have to have a band pass filter of certain characteristics, and then the final output will be KMT cos omega c. So that we can look at here. So after passing the MTCT through an appropriate band pass filter, we can get this first term, okay, 4 upon pi MT cos omega CT. So again, you do not bother about 4 upon pi, okay. It is one multiplicative factor. So I can consider it to be a like AC dash, okay, AC dash. So whether it is Ka mt cos omega ct or 4 upon pi mt cos 4 cos omega ct, okay, it doesn't matter, okay. So ultimately we are going to get the product of massive signal with the carrier signal, okay. So 4 upon pi mt cos omega ct. So this way we are going to get our DSB-SC signal. So I hope this discussion must be clear. If you find any difficulty in understanding this one, please try to derive this equation. Okay, I have directly used the result. Okay, so those who have sufficient background of the signals and systems, okay, please try to derive this particular equation. You will get this derivation in any of the books, okay, of signals and system. Here we just need to have the final result, okay, just that's why I have just used the final result. Fine. So this is our final DSB-SC output. Now after having this ring modulator, I would like to just emphasize that other than these two modulator like balance modulator and ring modulator, we can also have the some other methods that will be able to generate the DSB-SC signal. So that is our non-linear devices, okay, our non-linear devices, band pass filters, okay. Basically what we can have is we can have any particular massive signal, okay, XT, and then we can have a particular non-linear device, okay. So this non-linear device will have a certain characteristics, for example A0 XT plus A1 X cube T, okay, and so on. Any kind of characteristics will be there, okay. And because of this characteristics, as I have already explained you in the case of envelope detector, okay, if you remember that the discussion of the envelope detector, you will again find a certain nonlinear device with a certain characteristics, and if you substitute the value of xt, then you can calculate the yt. It is followed by a certain band pass filter. Then we can eliminate the unwanted portion of the signals, and then we can only retain the desired signals, okay, like which is going to give you a DSB-SC signal, okay. So it is not just this example, okay, just for your sake of understanding, I have written this particular characteristics like yt equals to a0 xt plus a1 x cube t, okay. It can be anything else, okay, anything else. We can design any nonlinear device, okay, that would be able to give you a certain product term, and then we have to design an appropriate band pass filter to just select that portion, okay, and that will be going to give you the desired DSB-SC output. So please try to practice this one, because I have already explained you about the envelope detector, okay. In the envelope, I'm talking, I'm saying about envelope detector. It is not envelope detector. I have already talked about you about the square law modulator. Okay, a generation of the EM wave. So I have talked about the square law modulator. Okay, in the square law modulator, if you remember, I had talked about that there is a characteristic like the output equals to A1 V I plus A2 VI square. Okay, so that was one of the characteristics that was able to give the conventional AM signal. Similarly, we can have another characteristics that will be able to give the DSB-SC output. So please try to see this one, okay, and you try to also obtain the DSB-SC signal using this non-linear devices, okay. So I hope this discussion must be clear. In the yesterday, in the last video lecture, I have shared you some important numerical problems related to our conventional AM, okay, or DSB-SC. So please go through those numerical problems, okay. They are very important. If you have gone through all the lectures, you would be able to solve those problems. And if you have any difficulty in solving those problems, you please uh, you can drop me a message in the comment box. So in the next lecture, I am going to talk about the single sideband modulation SSBSC. Okay. So please stay connected with the channel for getting the updates. So thank you for watching. If you find any difficulty, let me know with your comments. Thank you.